Milky Way by Shinga. The Milky Way is fun-sized, as a candy bar says, swirling in my mouth and swirling overhead. Millionfold stars, banded in one luminous light, what a glorious sky to behold brightly tonight. Ancient myth-tellers, filled with awe, knew not what they were seeing. We believers of science today know, and yet share the same feeling. All right, I gotta say,
Perfect.
that wasn't my perfect, so says the person in the background. But do I really think so? I wrote that in the last 10 minutes, so I gotta say, for that amount of work time, it was not bad. By the way, you can find this poem, if you really want to know, at this wonderful website, which is where I do my a lot of my poetry and stuff on Medium. So shinga86.medium.com/Milky Way. You can read it right there. But who is this voice right now talking? It is I, Shen, and you are watching SG2.
Yeah. What are we watching? What is this?
Yeah. So what are you watching? Right. It's always a good question. You are watching SG2 on Space, the only weekly space show. So hopefully you're watching on YouTube.com/Eshinga/streams. I'm using a different computer today, but it's the same people naturally. But my I don't know how well the colors are showing. The disembodied voice in the background. If we want to bring him, do you want to appear?
I do.
You do want to appear. All right, you have appeared.
Abracadabra.
Abracadabra. Abracadabra. There you go. And it's right there.
It's supposed to be a kind of onomatopoeia, or it's supposed to sound like some kind of Arabic invocation.
Understood. Let me continue on a little bit. This is SG2 on Space, the only weekly space show, episode 186, where we're going to be talking about the Milky Way Galaxy today.
Really?
Myself, Shen, and that person there is Dr. Leonard Kramer. And before I go on, gotta say you can support the show on patreon.com/SG2 on Space. And let me thank our past supporters and patrons, including my previous producer, Atum Ron, but patrons, Kyle Baker and Sam Welsh. And like I said, support show, patreon.com/SG2 on Space. Today's episode, we're going to talk about the Milky Way Galaxy, because not because of these candy bars, although that's pretty nice, but rather, in fact, I might eat one in the middle of the show if I get.
Not me.
But
carbohydrate.
It's because Leonard wanted to. You brought it up, and also it was a good topic because I although this night sky here isn't that great. I was in the desert a few weeks ago, and it was beautiful to see the Milky Way.
Yeah.
Over, just stretched across the sky, just like that.
Yeah. I think I remember the first time I saw it. So, I hope that if we have any of our audience gets a chance to see it. So, so did you have a question about it? About the Milky Way?
Sure. Like
what is it?
What is it? What are we seeing? Like when we see overhead and we just see this band of stars, like what is that?
Yeah. Well, the Milky Way is the galaxy that's our galaxy. That's where our solar system is located. We are not in the center of the Milky Way. I think in the 18th century, when people were really first starting to form good ideas about what the Milky Way was, that it was it was actually made out of stars, and that it was stars that were very, very far away. That some of the first efforts to map it actually were done then, and people thought that we were at the center of it, but it turns out we're a little off from it. But you can see it, and you need to go to a place where the skies, you're very, very far away from the cities, and you will see this. I remember the first time, and I saw it like that. That actually makes it seem a little brighter than it really is. But out in Texas Hill Country, for example, at night, if the skies are clear, you'll see something very much like this, and you're astonished at how broad it is and how it stretches from one side of the sky all the way across, and all the way across to the other horizon, and it's like, oh, that's there, and it's there all the time. And people in ancient times knew about it, of course, because they didn't have city lights and they didn't have artificial lighting inside their houses, and they would go out at night and look up at the sky, and they knew about this thing. And so there were all kinds of myths in ancient times that were were
Tell me a little bit about the myth.
Oh, well, in the Western tradition, it gets its name from a Greek, several Greek myths that are attributed to the heroic figure Heracles, who we know as Hercules in the Latin language, but Heracles was, and I don't remember why, but for some reason he was placed on by his parents on Hera's, who was the queen of the gods, placed on her breast, right? And so he was suckling while he was an infant at the time, and so when she woke up, she like, hey, what's going on here, and like pushed him away. And so I think that's how it's thought that Heracles or Hercules got his great strength and great power. But anyway, some of the milk from her breasts, sprayed out over the heavens, and so that's the so.
What an interesting story.
I think that's a pretty interesting story. So there's other myths about it, like in Native American culture. I think the Cherokee people, they have an idea. They said it's like cornmeal that's been strung along by a dog. Like a dog grabbed a bag of cornmeal, and it's a folktale, and then he dragged it across the sky, and so that's pretty neat.
You know the since I'm of Chinese ethnicity, you know what the Chinese myth is?
I don't know the Chinese one. I think in Japanese mythology, it's
probably very similar to
it's
the
some
Japanese
kind
mythology.
of river that separates two lovers.
Yep,
and so
exactly.
Maybe the Chinese myth, because the Japanese
it's the same. It's between the Weaver girl, which is symbolized by the star Vega, and then the cow herd guy, symbolized by the star Altair. So despite their love for each other, their romance is forbidden, right? And so they were banished to opposite sides of the heavenly river, and that's what the
mythology that
they're not known as, it's not known as Milky Way in Chinese or Japanese. It's like the river of heaven.
So it's really cool. I think I read that in the Polynesian, in the Polynesians, they were great navigators. They would travel thousands of miles between, and so they were looking at the stars all the time. And so they thought that it was like a shark or some kind of predatory fish.
Really?
Somehow,
It's different.
And it would somehow lead you to the afterlife. I'm probably.
You know what's crazy? Okay, so
what?
this Chinese. Sorry, it may not be that crazy, but actually, let me tell you something.
Yeah.
So, as you know, a couple of weeks ago, I went out in the desert, right?
Yep.
You probably know that.
Yeah.
And so one of the strange things that interesting things that was done was we were trying to. Okay, you may find it kind of a little weird, but we were doing like stargazing meditation thing. So where we picked a star, and then we're supposed to like hold out our hands, like energy stuff or whatever, and then supposed to like meditate to that star. And I wasn't even thinking about it, but I chose the star. I think I chose the star like Altair, and I was also possibly going to choose the star. And Vega was like directly overhead. And those two are the stars represented by the Chinese and Japanese myth. I just thought about it.
Wow, so, that's cool.
I mean, I was just random. I wasn't thinking about the myth. I was like,
I guess that would be one of those things that like serendipity, or like Carl Jung talked about stuff like that, things that would appear. I never quite understood whether it was like a mystical thing with him, but that would be a thing where something serendipitous occurs, where you connect to an ancient myth unconsciously. So
and it was I mean, I don't know, like it was it wasn't a conscious decision. I think it was just like they were convenient stars that I already knew, and they were beautiful and bright. So, but let's talk about the science a little bit. I know we like to talk about the myth.
Nobody knew anything. Nobody really knew what it was until Galileo observed it, and his telescope. Of course, we bring up Galileo a lot. So, and 1610 was a very productive year for him because I think that's when he started to write about it, and he said that it's a lot of tiny little stars. So he was able to determine that it was a collection of stars that were very, very far away. I don't know what else he said about it. I think in the 18th century, around 1750, 1755, the person who's otherwise known as a philosopher, Emmanuel Kant, who was also sort of a polymath, he thought he had this idea that it was a collection, that the collection of stars were being held together by gravity, right? So that was pretty. That was very insightful, very, very a good insight. And then I think later there was a scientist known by William Herschel, and so William Herschel discovered Uranus. You notice how I pronounce that, Uranus. He discovered Uranus, and but he also started to he had a really good telescope that I think he made it himself, and he was very carefully gridded the sky and tried to map all of the stars, or as many stars that he could in the Milky Way, and so he was able to map it and kind of had the intuition, or was able to infer that it was sort of a flattened disk, right? So that actually very cool, that in the 18th century that people were that they were able to do this kind of work to determine that at least it was a flat disk. He thought, and he was kind of the guy that thought that we were Herschel, William Herschel.
William Herschel, exactly.
William Herschel. It must have been about the late 18th century, 1780 something. He figured out that it was a flat disk, and he thought we were at the middle of it. What he didn't know was that when you're looking at the Milky Way, actually you see some voids, some areas where you don't see any stars, and they're sort of strung out, and that's a lot of non-luminous material like dust.
Hey, I want to bring up a question from one of our audience members. Shall we?
Okay.
I will briefly interrupt. So Joe Higgs asked, how many, this is a good way to have audience participation.
300 billion.
How many? 300 what?
300 billion.
300 billion.
What did I win?
No. I'm asking you. Well, the question, I'm just going to read it. How many light years away is the furthest part of the Milky Way?
50,000.
And how close is the closest part to our solar system?
50,000. About 50, because the long part of the disk is about 100,000 light years across. It's about 10,000, and don't hold me to this. You might want to check me, but I'm pretty sure about this. It's about 10,000 light years thick at the middle, and there's sort of like a halo kind of effect that's made out of stars. It's more tenuous. That surrounds the center of the galaxy. So it's made up of something like 300 billion, maybe 400 billion stars. I don't think anybody really knows exactly, but so I'm gonna say because we're sort of in the middle-ish. So the farthest region away from us is going to be on the order of 50,000 light years, and that's for the the main part of the Milky Way that we usually view as part of that. And like I said, there's kind of like a halo around the center. There's a black hole in the middle of the in the middle of the Milky Way, as there are in most galaxies. The Milky Way belongs to something what we call the local group.
What is the local group?
The local group is a group of, I think, about 80 some galaxies that includes the Andromeda Galaxy, which is that's a night sky object that people can see. And then there's also these things called globular clusters, right? Recently, within the past, some very careful work recently within the past 20 years or so, not quite 20 years, the structure of the galaxy has been revised. It's thought that there are really only two large spiral arms and a long bar that goes through the middle of it. And this is that's a thing that we observe. So it's in other galaxies. So there's like families of galaxies, and our Milky Way belongs to the one that would be considered a barred galaxy. And there's two large. Yeah, you might be able to find and that was sometime around 2005. What do you got here?
Well, here, check this out. This is considered the local galactic group, right?
Local galactic group, and this group is gravitationally they're gravitationally bound. So they're kind of like they're not really part of what when we talk about galaxies that are very distant and they're being stretched apart because of what we've talked about, the Hubble expansion, the cosmological expansion. This local group is not subject to that, because even though they're immensely far away, they're held together by gravity. And Andromeda and the Milky Way are on a collision course, and sometime in the distant future, tens of millions of years, they will collide, and they will form another. And actually, when galaxies collide, it's not really as devastating as it may seem, because really the stars are very large, but they're very tiny compared to the space that's in the galaxy. So they actually will come together, and very few of the stars will collide. So Andromeda Galaxy is bigger than the Milky Way Galaxy, and we have a lot of these things called globular clusters that are around the halo. And these were important. Prior to about 1920, it wasn't even known that there were other galaxies.
What did people think they were?
Well, people saw these nebula, and they didn't know how far away they were. They thought that obviously they had the notion about the Milky Way because of the careful astrometry, measurement of the stars and so forth. But they didn't know. Up until about 1920, there was a debate about this, about how far away objects were. And so in fact in 1920, there was something called the Great Debate, and there was two astronomers. I think one of them was called Shockley or Shapley. See if you can find the Great Debate of 1920. Google that for me. I think Shapley.
Great Debate of 1920. Wow.
About the Milky Way. It was a guy named Shapley and somebody else.
You got the name right.
And one of them
Curtis.
Curtis
and Shapley.
The Shapley-Curtis debate. Okay.
Yep.
Yeah, and one of them was right. One of them thought that the nebula that we're talking about in that local group that you were showing, he thought that they were immensely far away, and because he had done the work that Henrietta Levitt, remember we talked about Henrietta Levitt?
Yeah, we did.
And it all comes back to Cepheid variables, right? And the cosmological scale. So one of the big issues about astronomy has always been, like, how far away are the objects? Because a really bright star, all the stars basically just look like little pinpoints. They look like points. So you can't so you can't really resolve, how big it is, per se. You have to infer how far away it is by how bright it is, but you don't understand. We don't know what its intrinsic brightness is, because like an object that's very bright but far away will look just like an object that's not as bright but closer. I mean, I guess that's obvious, intuitive. But Henrietta Levitt, we've talked about her before. Um, she worked at the Harvard College, um,
Hmm.
under Pickering. Pickering.
Can you
So
explain a
what?
little bit how cepheid variables prove that
Yeah. So the
there's
cepheid
multiple galaxies?
variable is a kind of star that has a period to it. So it's bright. It gets brighter, and then it gets dimmer, and then it gets brighter, and then dimmer. And then, so it turns out that the bigger it is intrinsically,
Hmm.
the slower it does that, right? So she was able to measure the period, and the period's like weeks or months, so on the order of weeks or months. And so she had these photographic plates, and she could measure how bright the star was, right? From where we are, and then graph its period, right? I think,
Oh, like
yeah,
this? What
yeah,
you're showing?
period of
I'm showing here.
variability. Yeah, yeah, like that. And so that gives a scale, and it's a beautiful straight line. And they published that in the paper, and and so this became Levitt, the
So
Levitt
okay, so
scale.
like here the LMC is a large Magellanic Cloud, which is
Uh-huh.
a different galaxy, right, than the Milky Way.
Well,
So
I think that large Magellanic Cloud is one of those globular clusters that's
right.
around the
So
halo.
if we
Yeah,
look at that, are you saying somehow looking at this, they were able to figure out, hey, those
right.
objects were
We're
not in the
able to
Milky
tell
Way?
from the apparent luminosity of the apparent apparent means how bright they appear from where we are, right? And then
Right,
you could plug
right
it
here.
into that and tell, and then you also have an independent measure of of how bright it is, because of this scale. So you could watch it for a while and then measure its period, and then go in here. You could find its intrinsic, its natural uh, brightness if you were close to it, and then compare that to how bright it appears to you from far away. And so these were done for some. This was done for some nearby objects that could be independently verified through parallax. What's parallax? So parallax is an independent measure of how far away something is by looking at an object that is
Hmm.
that changes its apparent motion because the Earth has moved in its orbit. So if you look at an object from one side of the orbit to the other side of the orbit, then the apparent location of an object that's relatively close by will shift a little bit. And they were able to observe this, and they were able to observe it for cepheids that were close by. So that gave that pinned the scale. That pinned an absolute scale. You can't do parallax for things that are very, very far away, because the angle's not big enough.
Right, it
And
barely even moves.
in fact,
Exactly.
that was one of the things that the
Right.
Roman Church was complaining about Galileo, because they said, how come we don't see any parallax? Well, they didn't see any parallax because the instrumentation wasn't accurate enough to be able to
Right, right.
discern it, and the
But if
stars are
we,
far away.
you're saying if we look at this, they were able to say, for like, for instance, I don't know, this one, this orange
Yeah,
one, like it's within like, let's just say 1,000 light years away, whereas the LMC one was like, I guess it couldn't use parallax there, but it was still
right.
about
Yeah,
the same brightness, say,
yeah.
and
I
then
think people
yeah,
get it. I mean, I guess I said
I
it.
get it.
I was talking pretty fast, and I used a lot of words there, but basically you could go into that graph, and
Mhm.
so you look at the star for the Cepheid variable for a long time, and you measure what its period is. So once you know its period, then you go into this scale, and then this is the Levitt scale here. It tells you what its intrinsic brightness is. You see the
Mhm.
luminosity, and then you look
Mhm.
at its observed. You look at what its luminosity is on your photographic plate, and then you kind of like do a ratio of those two, and it tells you how far away the object is.
Right. Okay, that makes sense.
Yeah. So This was groundbreaking, and it was either Shapley or the other guy, Curtis or Shapley. Did you say Curtis? Shapley or Curtis? So I think
Shapley argued the universe was comprised of a single galaxy, while Curtis held that it contained many galaxies.
okay. So
Unless he
Curtis,
was right.
right? So
Curtis.
Curtis used the Levitt, this thing that we're this Levitt, not Levitt,
Mhm.
Levitt scale
Levitt scale.
to examine objects like in at Andromeda or other objects, and found that they were very much further away, and he published that, and so that was sort of a that was groundbreaking, because that like opened up people's ideas about, oh my gosh, the universe is much bigger than we thought, because people thought that just the the Milky Way galaxy was the universe, you know,
Yeah, Milky
and of
Way
course
seems
they
large enough, right?
I
So
mean
it wasn't.
they did see the Andromeda galaxy and other galaxies because they had good optics, they had good telescopes. Um, even
Mhm.
even in the 18th century, they had good telescopes for viewing things. They didn't have photographs then, so photography really helps a lot. But so that's that was a groundbreaking kind of thing, and it and it's all related kind of to the topic that having to do with the Milky Way. So the Milky Way, like the Milky Way, I have read that the Milky Way there's some inferences about the very early um, evolution or the origin of the Milky Way, and um,
Yeah,
the
how
James
did our Milky
the
Way
so
form?
so the James Webb telescope, infrared telescope, which is an infrared
Mhm.
telescope that's in orbit around the L2. We talked about it before, but anyway,
Oh, 2 point. Yes, let's not.
there's some
Mhm.
fantastic results that are coming out right now. It really is going to pay off, because we're seeing things that are much further away than we've ever seen before, and it seems like there are fully developed galaxies that are only 400 million years, less than a half a billion years from the Big Bang, and I'm not sure what to make of that. That it seems like there's not enough time to really form these fully developed objects. But um, so so the Milky Way galaxy has this halo around it, and it also has the little globular clusters, and in the middle there's a black hole. So it's quite
Hmm.
plausible that all the galaxies formed very early from black holes. And
Really?
yeah, that all of these galaxies, that supermassive black holes
Hmm.
that are at the centers of many of these galaxies are sort of the seed that created galaxies.
If we
And
look at this, Big Bang, Dark Ages, whatever that means, hydrogen reionization, the first galaxies, helium reionization, quasar era, and then sun forms. I guess
yeah,
supposedly somewhere here.
the James Webb telescope is able to look back into this region now. And so that's some of the things that I read. I read the other day, and this is very recent. Within the past month or so, there's a paper that's come
Mhm.
out, or a couple papers that have come out, where there's three or four objects that appear to be a thing called a dark star.
What's
Um,
a dark
a
star?
dark star is not really dark, but it's made out of dark matter, or it's thought to be. I mean,
Hmm.
making some inferences about the nature of dark matter. Dark matter is that mysterious substance that seems to make up 85% of the matter in the universe. So it's kind of important. So
Right.
it's thought that in this early period, um, that the dark matter was much denser than it is, and that it may have been able to coalesce. And then the other inference is that when dark matter particles, which are nothing that's ever been observed, but the inference is that they have to be made out of particles, because everything else that we know of, kind of is comprised of particles, and we have a standard model and all that. But that when the dark matter particles collide, that they will annihilate and produce gamma rays. And so that's the source for these stars, these very strange stars. I think they were
these things
calling,
are known as dark stars.
yeah, a dark star. We weren't going to talk about that, but that's kind of how we do our show. I mean,
Well, I mean, you can
Yeah.
talk about it if it's related to the.
or not.
Is it?
I mean,
do they still exist today?
that I think so. I don't know.
Nobody
It could
knows,
be
I
that
guess.
they eventually evolve into galaxies, or something like that. But they're not black holes. And then it raises the question about what does how does
Wow,
dark matter
incredible.
what?
No, I'm just
Yeah.
reading a little bit about it, but go ahead.
Yeah, so dark star. So the black hole originally the term black hole kind of started around 1967, 68, and some people referred to them as black stars. And so in some of the science fiction shows and stuff of that era, you'll hear about this thing called a black star. Now I'm kind of off topic a little bit. You'll hear this
Well, it's
statement,
interesting stuff. Go on.
so historically in the 1960s, when the notion of a black hole was really developing, before any of them had ever been observed, um, the they were sort of transitioning from calling it a black star to a black hole, and so in some science fiction, notably Star Trek, there's an episode of Star Trek where the Enterprise goes back in time to 1968, as a matter of fact, and they
What
use
happens in 1968 with Enterprise going back?
well, that's an episode that where apparently an alien from a super advanced race is trying to save the Earth by scaring them into submission, by scaring them into maybe having a nuclear war, because NASA is about to launch a Saturn V and with nuclear. But that I'm getting off the topic.
That's
we can talk about that another time. But
question.
anyway, they use this term black
All right.
star. Okay, and so and they really meant black hole, because so that I don't even know why we're talking about, but I guess it's sort of
Well, okay. So I think
entertaining
you were
and interesting.
mentioning about like dark stars, and then I just kept asking you about things
Well,
like
yeah. So black star. So dark star is a new thing. Okay, that's something
dark
that's
star
come
is a
out,
new thing.
and it's something that has been inferred that may be the nature of dark matter. If we make some assumptions about it, that it might form a structure that's a dark star. But it actually is not dark. It's just the dark star just means that it's comprised of dark matter that's being confined by the gravity and being held up against complete collapse into a black hole by the reaction of the dark star with itself. So you see, and
really
they've got these really neat names like neutralino.
neutralinos.
I think it's like it
Dark
reminds me of like
star.
some kind of food you could buy at a
I
street
know.
vendor
I was just thinking that
in
the stars
Italy.
would be composed mostly of normal matter, like modern stars, but a high concentration of neutralino dark matter present within them would generate heat by annihilation reactions between the dark matter particles.
Right.
This heat would prevent such stars from collapsing into the relatively compact and dense sizes of modern stars.
So I don't know if that has to do with the formation of galaxies exactly, but where I was going with the galaxies, I think a lot of that's not really complete. How galaxies form, I don't think that's completely understood, but we're right on the cusp of making all new observations of the very early universe to discern those things. But some of the thoughts are that our galaxy has already gone through several collisions with stuff in
Mhm.
with other galaxies in our local group. Some people have even surmised, where some of the remnants are of that, and so some of the
Are
other.
you saying that our galaxy? You're saying our galaxy is formed from a bunch of other collisions with other galaxies?
Not a bunch, but
A few.
a few, and
Okay.
two or three or maybe four collisions, and we know this because uh, Andromeda is heading right for us. Okay, there's no cause
We're
for
going to collide
alarm.
with
Okay,
Andromeda's galaxy soon. Well,
yeah,
millions of years from now.
hundreds of millions of years from now.
Hundreds of millions of
Yeah,
years.
so
It's going to be
so
great. We'll be
yeah.
dead by then.
Well,
I mean,
yeah, the
okay.
robots will rule the earth,
Look,
and
it'd be, I guess these two are
that's
like,
a thing. Yeah,
yeah, that's the thing. These two
yeah.
are colliding. That's going
and
to be
and and they're
us and
bound
Andromeda.
gravitationally, and also there's some interaction between the gases, the dust and the gases, and
Mhm.
those will ionize and maybe glow to a certain extent. But by and large, the probability of anything catastrophic happening to any of the solar systems there is quite small, as paradoxical as that may seem. So they don't exactly pass right through each other because they are gravitationally bound, and that interaction will coalesce, will cause some of the stars to come closer, and some of the stars will be thrown out, and so forth. But I think in the evolution, the evolution of galaxies has something to do with early formation of very massive black holes. I want to say 1,000,000 times bigger than the sun. You can check on that. I can't remember. It was something a stunningly large number. So all these galaxies, most of them appear to have a black hole in the middle of them. They are suffused with dark matter, which dominates their rotation.
What percentage of our Milky Way is dark matter?
85%.
85%. That means
Yeah.
85% is nothing we can see, and we don't even know what it is.
Yeah. Okay. And
Don't know.
and shame on the string theorists. That's all I have to say.
Wow.
Because if string theory is a theory of everything, then you ought to be able to make a theory that fits the facts that fits the observations that you
boy.
have now, and then make a prediction about the future, or make a prediction. Or you might be able to look at your equations and say, "What's that? Hey, that's dark matter." And so it didn't pan out that way. So there's a lot of stuff we don't understand, and it's great, isn't it?
It's great that there's so much we don't understand.
It's great. Yeah, it makes makes life an
I mean,
adventure.
if we understood everything, we wouldn't be sending out telescopes and doing research and such.
Exactly.
I guess.
Right.
So it's good. So
Yeah.
this, I mean, I guess depends on the person. This guy says like 45% from dark matter here, but you're right. Other people have said like 80% or 90.
No, I don't think it's 45%. I think that's too low. I think that it's more on the order of 85%.
Okay.
Yeah. So, I mean, I could be wrong about that, but
No.
But anyway,
I'm
the
not
shape
saying you're
the shape of the galaxy, of our galaxy, it's kind of like there's a bar which is sort of bulbous. It's kind of
wrong.
shaped
Mhm.
like a peanut, right? And then it has some arms that are some spiral arms that kind of spiral around in both directions. It used to be that we thought it was like a pinwheel, more or less, but as of the past 20 years, we've come to understand more about that, and using radio astronomy, and
You want to say
very
something cool?
of course. Are we
Let me see.
gonna change topics?
Not yet.
Yeah, it's something like that. And so the thought is that there's really only two. Well, I said only two, but mainly I mean those two main arms, and then it's populated in the middle, but that's the bar, right? So some of the pictures
When
I've
we
seen.
see when we say like that initial picture I showed,
Yeah.
when we see the Milky Way galaxy, we're really seeing through the middle, right?
Yeah, well, we can't see the middle because there's a whole lot of dust in the way.
Okay, so what are we seeing? We're seeing one of the arms, right?
We're seeing the arms that around our local area,
We're
group.
basically seeing like maybe like this arm or something.
And William Herschel, even in the 18th century, he mapped a lot of those stars. It was a pretty amazing thing he set out to do.
Mm-hmm.
He took graph paper, right, and then he split up the night sky into 600.
Graph paper.
Yeah, 600. He took graph paper, 600, and then every night he would look at a different square, and then map the stars that he could identify. And I think he did tens of thousands of stars, and then he was able to sort of map out a structure, but he only saw that little region that's right around us there. See where it says we are here. And of course,
we are here.
Of course, we don't have a picture like this. Okay, this is a drawing.
We're inside the arm.
Everybody know. I guess everybody knew that, but we can't see that, but we can see the stars, and then the stars that the discrete stars that we see. They're close in. They're right around us. So there's nothing mysterious about that. But the evolution of this object, I think, is still quite up in the air, and how the origin of it, and so forth. So
yeah, this is what I'm saying. Like this beautiful view here,
and people
really just this band here.
Yeah, our audience needs to get out and find a way to see this. If you
where can you go to see such a sight?
Well, you need to get away from the city, and you need to have good, clear weather. We're in Texas, so running out to hill country out west of San Antonio. But where we are in Houston, the air is usually so hazy, just naturally. I mean, it's very hot and humid, and so it's quite rare. And then we're in the fourth largest city in North America.
Yeah, it does not work very well.
Yeah.
Trust me. Living in the city has led me to actually, even working in the space industry, I don't actually look up at space that much.
Yeah. I mean, there's a lot of good things about it here too. So
right, but if you go out in the woods or in the desert, like I was in Sedona a few weeks ago, you get to see stuff like this, which is absolutely beautiful.
I've seen it from out west of San Antonio. I've seen it from the Big Bend country.
Now you're probably never going to be able to see this, though.
I've seen it in Maine also. Yeah. I think the first time I ever saw it, I believe the first time I ever really saw it in all of its glory was on a trip to Maine.
Hey, I like this website. Look at this. Imagine if the Milky Way Galaxy is a pepperoni pizza, because I enjoy eating that. All the stars that we can see from Earth are only within one pepperoni.
Yeah, something like that. Right.
Wow.
That's a good way to express that.
You can teach kids that.
Yeah. And so those globular clusters, they have something to do with so there must have been some kind of spherical or oblate spherical kind of object that formed that was sort of tenuous, and that as it collapsed, different parts of it started to collapse into different sections, and so that's the origin of the central part of the Milky Way, and then it had some angular momentum associated with random fluctuations in the primordial time, and so it had some. That's the second time I've said that word.
I like that word.
Yeah, I said it last week. So
you did. Can I ask you a question? What is going on here?
Well, this I don't know. This is these look like velocities.
I think that's what it is. So our sun is actually going around the galactic center.
Yeah, I guess we should mention that. Yeah,
sun is not staying still.
No, this whole thing is orbiting. And I used to think that it was just regular Kepler orbits, that were disturbed, but it turns out that it's really not orbiting like objects in orbit. It's almost like a solid rotation, and that's attributed to just a mass of dark matter that extends for hundreds of thousands of light years away from the object. So we kind of exist in a bubble of dark matter that extends much bigger than the extent of the than the extent of the galaxy that we can see. And we know that because it stays in almost solid rotation. It rotates almost like a phonograph record, if you know what that is.
Yeah. Okay. So it's like, instead of us imagining, I don't know, something just out in space, just rotating around, it's imagine something all clumped together, right? Like,
yeah, it's almost like it's in solid rotation, and that may be what this picture is supposed to show. Because if you notice the yellow vectors, I don't really know what this is, but I'm gonna assume that those are velocity vectors. And you notice that the ones that are out near the edge are about the same size, the same length as the ones toward the middle. And
position and velocity map. That's what this is, of the Milky Way galaxies. Arrows show position and velocity data for 224 objects used to model the galaxy.
Yeah. So it's not really quite in solid rotation. Solid rotation means that it's rotating around as though it were a solid body. It's not quite. I mean, it's still kind of fluid, but it's not rotating around like these objects were in orbit. And if they were in orbit, then the orbit, for example, Mercury is in orbit around the sun, and so is Jupiter. Well, Mercury orbits in 88 days, and Jupiter orbits around the sun in 12 years. So Jupiter is moving slower than Mercury. Okay, well, the galaxy rotates not quite like that. It rotates more like it's a photographic record, and so it's all solid rotation, but not exactly. Okay, so there is, it's not perfectly like
there's
that.
I think there's a beautiful video. If you let me see, I think I've shown you this. Here, let me see if I can find it. This thing. Okay. So picture this, right?
Oh yeah, so this is the motion, yeah.
Yeah. Like, those are all the planets and asteroids and comets, whatever, rotating around the sun. And so it's a very dynamic system. And our sun is, meanwhile, it's going like that.
Yeah.
Like,
it's a beautiful animation.
Yeah, the sun is like a comet dragging the planets in its wake. Sort of. Not really. That's just.
There is a magnetosphere to the sun. So, and the motion. That's one of the interesting things that they could show here, is that when you get very far away, the atmosphere of the sun is like the solar wind, which we've talked about before, and that's spraying out all the time, right? And it's coupled to the plasma, so it's an electrically conducting fluid. It's mostly protons with electrons, and so it has an embedded magnetic field that expands away from the sun. But then the proper motion of the sun, and actually all the stars, through the interstellar neighborhood tends to create a kind of like a bullet-shaped, maybe a bullet, or a bullet-shaped void or cone that travels through the interstellar medium, and it manifests itself with like changes in the nature of the directions of the magnetic field and the plasma density and so forth. So
that video, for better or worse, did not show that, but
well,
I think it was kind of cool. So the solar system moves through the galaxy with about 60-degree angle between the galactic plane and the planetary orbital plane. That's interesting. And so the sun appears to move up and down and in and out with respect to the rest of the galaxy as it revolves. That's
a thing, yeah. And all of the solar systems are doing that. I also read somewhere that the relative size of the solar system is like if you had a CD, a little CD. If that was the solar system, then the galaxy would be about a little bigger than the size of the Earth. I'm not sure. I haven't checked that calculation, but so the rate
Okay.
the size of the solar system
Mm-hmm.
is the size of the solar system to the dimension of the galaxy is the same as the size of a CD disk to the diameter of the Earth and
Wow. Okay, so this picture is obviously not to scale at all. So
yeah, I'm glad that you
but,
pointed that out. Yeah.
But at least it shows how the planets are orbiting, so to speak.
So they're going up and down, right?
Yep. So what was I going to say? What you were saying just now is that the solar system size relative to our Milky Way galaxy is like the size of a CD, like maybe this big, relative to the entire planet.
Yeah, something like that.
Yeah.
Now that's just something I read, and I don't know if it's true or not, but I'd have to check it. But
well, it sounds about right. If you look at the ratios, I suppose we can easily calculate it.
Yeah. So
pretty incredibly small we are on this tiny little world.
Anyway, that's kind of all that's all I can think about to talk about. We talked about Emmanuel Kant and Herschel and the Curtis Shapley
the 1920 debate.
1920 great debate. We didn't talk about Hubble. Hubble sort of confirmed all that stuff by doing the redshift stuff in 1930. So that was pretty spectacular. We did talk a lot about dark matter. So dark matter actually, the evidence for dark matter actually also appeared in the 1930s. There was a guy named, I can't remember. I think he had an unusual name, but he used what they call virial equation. In other words, he looked at a particular globular cluster that had a lot of he was looking at the redshifts and calculating the velocities of things, and then he figured out what the energy was. And so he said, hey, there's not enough mass in this galaxy to support the velocities that I'm seeing here. And I think, and that was in the 30s. What?
Do you see what this is?
Yeah, that must be is that our local group?
No, it's, oh wait, maybe it is. Local group, great attractor, dipole repeller, Shapley attractor. Relative attractive and repulsive effects of overdense and underdense regions on the Milky Way. The combined effect is known as a dipole repeller.
Okay. I don't know.
Not quite sure. I guess this kind of indicates like what is this like a?
I usually don't think of gravity as having any kind of dipole character at all. So there's only the gravity only has one polarity to its charge. It's like the charge.
Attractive?
The charge it's an attractive charge. So
why is this called dipole repeller? What could possibly repel it?
I don't know. I like that website, Big Think. So I can look at that, but not tonight.
Maybe this is actually interesting. Oh wow. Dipole repeller is a center of effective repulsion in the large-scale flow of galaxies in the neighborhood of the Milky Way. It is thought to represent a large supervoid, the dipole repeller void. Gravitational attraction induces movement towards more dense areas, and at the same time, the gravitational repulsion pushes the matter back from an empty zone, according to the dipole repeller model.
Well, I could buy that. I think that's probably true. Yeah. So the absence of mass effectively gives you a net
negative.
Yeah, it kind of behaves like a negative. So plasmas behave this way. So. Yeah.
Oh, okay. I see. So like the red area here, an absence of mass, and here blue is like a supercluster, so a whole lot of mass. So you get induces movement towards a more dense area, which has more gravity. Got it.
Right.
So you can model it
and
as
so,
if it's being repelled.
So one of the things, one of the mysteries that I've kind of struggled with or thought about for many years is the nature, like it's a cosmological principle. We talked about the cosmological black body one time, and remember that we said that it's a black body to very high accuracy. Remember the cosmic microwave background.
Yes, a topic we go to a lot.
So if it's and so what that is that's that region that's 13.7 billion years ago that where all the matter in the universe kind of condensed and became transparent, basically. So we can't see anything back beyond that, although we may be able to use gravity waves to penetrate that someday. Some tentative steps in that direction, but anyway, so beyond the microwave background, so the fact that it is the most precise black body curve, the Planck, that Planck distribution at what 1.7 Kelvin or 3.7 Kelvin, at I think 3.7 Kelvin, which is microwaves that, well, it's visible light that's been Doppler shifted red all the way down into the microwave region. So originally it was bright light, but because of the cosmological expansion, it's been shifted down to microwave temperatures. And so, but it's the most precise, it's one of the it's basically the most precise black body that we can see. And every direction we look, it's the same temperature. And so that means that, like, it's a structure that was formed at the instantaneous. It's like a photograph of the Big Bang that's been spread out over the the width of the universe, essentially. So one of the things about that is that a black body implies maximum entropy, meaning when we think about, black body means in equilibrium, in thermal equilibrium, and yet we're not in thermal equilibrium. So we're observing something at the early portion of the universe that's in almost the maximum amount of entropy that the universe of something that we can examine, mainly a black body. And yet the universe is still evolving, right, according to the idea that entropy is low. So where we are, entropy is low and it's increasing. And so that's kind of a mystery, and I think gravity is the solution to that. Gravity is that with the creation, and somebody smarter than me might be able to articulate this better, and I keep searching for somebody smarter than me to say this, I mean somebody who understands this better than me would be able to say, look, all of the matter and energy is at maximum entropy within easily within 100 million years of the beginning of the Big Bang. But we're 13.7 billion years after that, and we're still evolving. We're not in a black body. We're evolving. And so the way that relates to galaxies is galaxies are condensing from a low entropy to a higher entropy state, so they're condensing, and so that's what happened at the Big Bang. Is the matter was distributed out, matter and energy was distributed out at high entropy, but gravity was kind of like left behind. And so now gravity is kind of like pulling things together, and we're sort of now thermalizing the gravitational, the energy that's associated, or energy and structure associated with the gravity. And it seems likely that dark matter has a lot to do with that. Dark matter won't interact through through normal, through electromagnetic or any forces that we know of, except gravity. And so, if dark matter was created at the beginning of the universe, then it's likely still very hot. It still has the same temperature as the um, as the original Big Bang. So anyway,
that may be true.
I don't know if anybody's following what I'm saying. I'm not sure I follow myself. I have some kind of thoughts about this, and it's mostly just like questions about about it. But anyway, that's all I was going to say. Did you possibly want to talk about any other topic?
Want to talk about?
What other?
I mean,
what
we
other
already
things?
covered like one of the biggest things in the universe.
Yeah. Where is there to go from there?
Let's see. What else? Should I show you a random video of what could possibly be a UFO?
Absolutely. Whoops.
I have not even seen this. So it's like I always just play some random video, right? Let me see. Does this work? Yeah. Okay, let's see how well this works. Let's see how well this works, shall we? It may not work very well. All right. I've not seen this video. I'm just playing it. Let's see what happens. Okay. Is it playing? Tell me if you see anything. So this supposedly happened in Argentina, I think. All right. So I've not seen this video. I don't know what's going to happen.
Okay. Well, now when you look up in the sky, I see I think it's a satellite.
Okay, I think is this a repeat of the same video, or was that?
I don't know.
Yeah, like what is that?
I don't know, Shen. It looks like it's a star. It's Venus.
It seems to be moving.
So an airplane. Have they not seen airplanes fly? So I don't know what's so unusual about this.
Wow, I mean, that doesn't look like an airplane, does it? It's like a round looking shape thing.
If you say so, that's sort of an impression.
I mean, look, see, how does that does not look like an airplane.
I concede that it doesn't look like an airplane, but it doesn't look unusual in terms of, well, maybe it has like a little
UFO casebook. I don't know. That's just some random woman, I guess.
That was a girl. Yeah. Okay.
Okay. So what is this? Peculiar arrow-shaped UFO has been captured on camera. The incident was photographed near El Escorial, Chubut, Argentina, hovering over the Patagonian plains in both horizontal and vertical positions. Local journalist Calaverita Matias shared the captivating images on social media, accompanied by the caption, "Best photos of a UFO in Chubut." Revealed the photos in. Okay. And some other. Yeah. So I don't know. I mean,
I don't know.
It looks like a round object that's moving. So
it does.
Doesn't it? Yep. I am not extremely convinced, and neither is Leonard, apparently. So, but of course, Leonard, you're not normally convinced of any of this.
Well, neither are you, frankly. I mean, it's like you're pinning it on me, but it's like I don't think that you're really.
Okay, you're right. I still got to go through.
I'll tell you. I want to believe, okay, but I don't choose what to believe.
Yeah. Hey, I found this.
You heard me say that, right?
Thing.
Yeah.
Yeah. Hey, hold on a second. I found this thing. You know what? These are like aliens. Like, okay, this is completely made up, probably.
Isn't this from a video game?
It looks like somebody made it for a video game, right? Like
this is
humans are here.
What is this?
And these are
what's the name of this?
Like different others, weird alien species or something. So the map depicts about half of the advanced or developing intelligence in the galaxy. Maybe, who knows? Maybe one day we will actually have a map like this. But right now, this is all speculation.
I hope so. I would like that. I would think that would be very exciting.
That would be interesting.
However, and I'm going to say it again, I don't think there are any. I think we're it. And if there are any others, they're very, very rare. They're incredibly rare. And the reason I say that is that I don't want to say irreducible complexity, but the notion that life just arises spontaneously is not
Yes.
I just don't take that for granted, because we don't know how to spontaneous. We can't even make things alive from dead things. If you take if you if you
There's
give
a
me
lot of things we can't do, Leonard.
what?
There's a lot of things we don't know how to do yet.
Well, I know that. Okay, but that's right. And so you take that as, well, there's a lot of things that we don't know how to do, and we'll know how to do them someday. And maybe so. Okay, but think about it the other way. If it was true that we could just put dead things in a box and then like set it out in the sun, and then living things would come out of it spontaneously, then you'd hear me say something different. Then you would hear me say, yeah, life must be all over the universe. If somebody, if Watson and Crick, who did, we should talk about this another time.
We should.
Yeah.
I always end up getting in a discussion with you about life.
Right, because people want to believe, and I want to believe. Okay, but judging or making assessments, critical assessment of the a priori, it's like a Bayesian kind of thing. We can talk about different kinds of stuff. There's so much to talk about.
There's so much to talk about.
And
but you know what? We go long every single time. Gotta say, look up, because you never know what you will see.
That's right.
Whether, naturally, if you live in a dark spot, you might be able to see the band of the Milky Way Galaxy.
Please make an expedition. Get out to the country and look up in the sky. And please, you must see that, and
you must see it indeed before you die, at least several times. All right. So remember to support the show on patreon.com/SG2 on space. Thank you to our past and present supporters.
Tell your friends.
And also go on youtube.com/Shingula/streams, or just look up SG2 on space there.
Yeah.
And it's subscribe, share. There
and
I
think,
that good stuff.
Aren't we on some other
We're also on Spotify, so you can go on there, podcasters.spotify.com/pod/show/SG2 on space. All right.
Okay.
And with that, I am going to have to say
namaste.
Namaste. Good night.
Good night. Mwah.